Imagine you are a part of a global manufacturing division. Your team just spent, 8 grueling months building this flawless hardware in the loop rig.
Right, what the industry calls a HL rig.
Exactly, a hell rig. And it is just an absolute marvel of engineering.
Right.
So you initiate the validation test on a Friday evening before you head home.
Which is always a great feeling.
Oh, the best. And the physical test runs perfectly all weekend long. I mean, it's simulating millions of operational cycles.
Doing exactly what it was designed to do.
Right. But then Monday morning rolls around, and your reward for this flawless physical execution is not, a celebration.
No, not at all.
You sit down at your workstation, and you are greeted by a completely crashed text editor. And sitting on your local drive is this massive 50 gigabyte text file containing nothing but raw hex strings.
Just endless walls of data.
Yeah. And you are now expected to sit in this quiet room, squinting at a terminal window, basically scrolling endlessly through millions of lines of machine code, all just to find a single, 12 millisecond voltage sag.
Yeah.
It's pure torture.
It really is. So today we are exploring exactly why we are deliberately torturing our brightest engineering minds with scrolling text. Welcome to today's deep dive. We are thrilled to have you with us as we unpack how one of the most celebrated schools of physical design can actually solve a massive, totally invisible crisis in modern software and hardware engineering.
Yeah, and it really is an architectural crisis, right? It quietly drains billions of dollars from the global economy every single year. But what makes this particular challenge so compelling is that the ultimate solution we're looking at in our source material today, it's not some, bloated new enterprise software suite.
Right, thankful. Yeah.
It is actually a radical return to foundational design philosophy.
Absolutely. So to guide us through this, we are pulling from 3 incredibly dense, just fascinating sources today.
Some really great reading.
Oh, yeah. First, we have a comprehensive EDN report detailing the 2026 landscape of edge AI. Second, there's this highly provocative engineering manifesto by Prasad Bande, and that one is titled The 50 GB Blind Spot. Such a good title.
It really is. And finally, we're pulling from an industry analysis, unmasking what researchers are currently calling the trillion-dollar corporate bottleneck.
Which sounds dramatic, but as we'll see, it's really not an exaggeration.
Not at all. So our overarching mission today is to take the legendary design philosophy of Dieter Rams.
Specifically, that core principle of less but better.
Exactly.
Yeah.
Less but better. And we're going to apply it directly to the infuriating, bloated world of industrial hardware testing and data architecture.
Which is desperately needed, because when we look at the reality of firmware-in-the-loop tests, like the ones described in Bond's manifesto, we really have to start by understanding the mechanics, like what is actually happening on that test bench.
Right. Set the scene for us.
So a hardware-in-the-loop rig, a HL rig, is essentially a simulated physical world. You take an engine control unit or, say, a flight controller, and you plug it into a physical bench. And this bench basically tricks the computer into thinking it is actually flying an aircraft or driving a car.
It's feeding it fake reality. Exactly.
Yeah.
The bench feeds it simulated sensor data, maybe, 10,000 times a second, and then it monitors exactly how the hardware responds to that data.
And because in engineering, we demand absolute precision, the sensors on that bench are capturing every single microsecond of the event.
Every single one.
But the output, and this is the crazy part, it isn't a neat summary graph. The analog voltages and the digital pulses, they are translated directly into hexadecimal code.
Right. Base 16 strings of numbers and letters.
Yeah, because that is the native language of the machine layer. So when the machine runs perfectly for 48 hours over the weekend, it is blindly translating 10,000 perfectly normal operations a second into these hex strings. And it's just dumping them into a log file.
Over and over and over. Which brings us to the sheer absurdity of the modern debugging workflow. The sources highlight this really profound mismatch between human biological capability and machine output.
Oh, it's so frustrating to read about.
Right. I mean, we are taking adults to whom we have awarded master's degrees in thermodynamics and embedded systems, electrical engineering, and we are basically asking them to act as biological CTRL plus F commands.
A biological search function. That is just...
That's exactly what it is. We force highly trained engineers into silent rooms, staring at these terminal windows, and we're just hoping their optical nerves can spot an anomaly hidden in 50 gigabytes of alphanumeric noise.
It's impossible.
It is. We hit a hard wall of basic human physiology here. The human visual cortex simply cannot process industrial data velocities. I mean, think about it. A human reads text at, a few bytes per second.
If that.
Yeah. Meanwhile, the hardware bench outputs data at megabytes per second. Designing an architecture that requires biological intervention at the machine data layer, it just violates the fundamental physics of human cognition.
It really does. And Bond's manifesto uses this analogy that I think perfectly crystallizes this physiological mismatch. He says forcing a human to parse this much machine output is exactly like forcing a parent to sit down and watch an entire month of empty driveway security footage.
Minute by agonizing minute.
Exactly, just to spot a single falling leaf. You are asking a human brain to maintain high alert focus on a perfectly static, totally unchanging environment for hours on end.
And, well, the inevitable result of that architectural choice is human failure. I mean, the human brain is evolutionarily wired to tune out static backgrounds.
We adapt to the noise.
Right. So the engineer will blink, their focus will drift, and they will scroll right past that 12-millisecond voltage drop. The software on the rig functioned exactly as programmed, right? By logging everything. But the operational architecture literally guarantees that the human will fail to interpret it.
And beyond just the mechanical failure of the task, we have to extrapolate what this does to human morale.
Oh, it's devastating.
It really is. Treating a brilliant operator like a biological parsing script, it completely strips them of their dignity. You know, you spend 6 years studying advanced mathematics and control theory, only to spend your Mondays manually scrolling through a text editor.
A text editor that is constantly freezing, by the way.
Right, because it literally cannot load a 50-gigabyte file into RAM. It's just a massive, massive drain on intellectual capital.
It's an industrial vanity metric, really. Companies love to boast about their data capture rates. We log 1 million data points a second.
Yeah, sounds great on a slide deck.
Exactly. But the downstream reality of that metric is a sleep-deprived developer hunting for a microscopic drop in voltage. So the question we really have to ask is, if this workflow guarantees human error, ruins morale, and completely stalls product development, why is it the industry standard?
Well, it's definitely not, because engineers have developed some sudden passion for reading hexadecimal code.
Definitely not.
So if the operators hate it, the persistence of this workflow has to be rooted in a structural design flaw. And according to the industry analysis we're looking at, this data hoarding is driven entirely by corporate psychology and hierarchy.
Yeah. The industry analysis explicitly names this the trillion-dollar corporate bottleneck. Organizations are finally slowly awakening to the fact that these massive log files are not badges of honor.
No, they don't represent rigorous engineering at all.
Right. They are a massive capital leak. But the leak is sustained by specific archetypes within the corporate structure, people that the report calls control point owners.
And these profiles are so recognizable. So the first archetype is the compliance officer, and their entire operational mandate is defensive.
Completely risk-averse.
Yeah. To a compliance officer, massive data retention equates to legal safety. If an auditor or a regulatory body comes knocking, they want to be able to point to a centralized server and say, look, we saved every single byte of testing data.
They demand these massive, unwieldy data lakes.
Right. But the tragic irony of this defensive posture is that by hoarding all this raw data, they mandate the creation of the exact noise that hides the critical product failures they're supposed to be preventing in the first place.
Exactly. They're literally burying the evidence under a mountain of useless information just to satisfy a checklist.
It's wild.
And then the second control owner perpetuating this mess is the hardware QA manager. Now, this is a fascinating psychological block.
Oh, I loved this part of the analysis.
Yeah, because this manager operates on legacy workflows. They spent the first 10 years of their career manually decoding hex strings and, suffering through these massive logs. So to them, manual log inspection is a rite of passage.
It's pure generational hazing. They equate suffering with diligence.
Yes, because they had to endure the pain of manual biological parsing. They believe the current generation of junior engineers must do the exact same thing to prove their worth.
Like, I suffered, so you have to suffer.
Exactly. They view automated filtering as this, shortcut that breeds lazy engineering.
Right.
But they're completely missing the fact that the volume of data has scaled exponentially since they were junior engineers.
Right. They're reading maybe a few megabytes back in the day. Now it's 50 gigabytes.
Totally different scale.
Yeah. Which
brings us to the third bottleneck, procurement paralysis. Because when an engineering team finally revolts and asks for, enterprise-grade log analysis software to handle these 50-gigabyte files, they hit a bureaucratic wall.
A massive one.
Enterprise software suites capable of ingesting and analyzing proprietary industrial data at that scale, they cost hundreds of thousands of dollars. And the procurement cycle takes, like, 18 months?
You need sign-offs from IT, legal, finance.
Yeah, and it involves incredibly complex cloud integration.
So the engineers simply give up.
Yep. They settle for broken text editors because suffering in silence is honestly just faster than fighting the procurement bureaucracy.
So we have legal paranoia, generational hazing rituals, and bureaucratic gridlock forcing this complete anti-design of data hoarding. But to break this gridlock, the sources suggest we need to apply first principles from information theory. So, how does information theory fundamentally challenge the compliance officer's mandate to just save absolutely everything?
Well, in information theory, there is this really foundational mathematical principle.
Right.
A perfectly repeating machine cycle contains zero information.
Zero.
Zero. It carries absolute zero analytical weight. Think about it. If a mechanical actuator is operating exactly to its mathematical specification and it repeats its baseline function flawlessly for 48 hours, the data it generates is mathematically redundant.
Right.
The machine is effectively screaming, "I am fine," 10,000 times a second. Recording that baseline behavior over and over and over again adds zero new knowledge to the system.
Okay, let me put myself in the shoes of that terrified compliance officer for a second here.
Sure.
Information theory might say a repeating cycle is zero information. But in a corporate environment, a deleted file sounds like a massive legal liability. If we start intentionally deleting the baseline data from our validation tests, aren't we violating corporate IT policies? I mean, how do you convince a compliance department that mathematically redundant data is actually safe to destroy before it even hits the server?
And that friction you just described, that is exactly why this bottleneck has survived for so long. But the solution presented in Prasad Brana's manifesto is so brilliant because it completely bypasses the compliance argument altogether.
How so?
The solution does not require breaking rules,
I've that.
and it does not require sending sensitive proprietary product data to some unauthorized third-party cloud for analysis. The fix happens strictly at the edge.
And by the edge, we basically mean the local physical environment, right? The actual machine.
Precisely. You process the data locally, completely offline, within the approved IT sandbox of that specific engineering workstation. You aren't exfiltrating data to a cloud server to find the anomaly. You are applying an intelligent local filter before the data ever reaches the permanent storage drive.
And this brings us to the technological shift that makes all of this possible. And this is where Dieter Ram's design philosophy beautifully, just perfectly, intersects with software engineering. We are talking about edge AI acting as the ultimate minimalist filter.
Yes. Let's really look at Dieter Ram's work at Braun in the mid-20th century. Because Rams revolutionized industrial design by stripping away all the non-essential buttons, the dials, the visual noise from physical products.
Like, he hated clutter.
He despised it, whether it was a pocket radio or, his famous record players. His goal was always to achieve functional clarity. He believed a product's function should be completely self-evident, which you only achieve by ruthlessly removing anything that isn't essential. Less, but better.
Less, but better. And Edge AI applies that exact physical design philosophy, but to data architecture.
Exactly.
Because by moving the artificial intelligence processing directly onto the physical hardware that's collecting the data, completely severing any reliance on the cloud, the system can act as an intelligent log copilot. It strips away the non-essential data noise right at the source.
Mechanically, the way this actually works on the test bench involves deploying an offline tensor model.
Okay, unpack that a little bit.
Sure. So this is a very lightweight machine learning model, and it's trained specifically on the expected mathematical baseline of the hardware. So it understands the standard operating deviation of the device under test. It knows what normal looks like.
Got it.
Because the model is executing locally, right there on the edge, it can analyze the high-velocity data stream in real time, and it instantly drops all the normal expected signals.
Oh, wow. So it throws out that whole month of empty driveway security footage exactly as it happens.
Yes.
And it only commits data to the hard drive during the 5 seconds when the leaf actually falls.
Exactly. It isolates only the statistical deviations, the anomalies.
Okay, but for anyone who has actually tried to run AI inference at the edge, you know the immediate wall you hit, right? Compute power and thermal constraints.
Oh, yeah. Always.
Because you can't just slap a massive, power-hungry server GPU onto a small industrial testing rig or a tiny embedded sensor.
No, it would melt.
Right. So how does this minimalist approach actually survive the really harsh physical constraints of edge computing?
That is a critical engineering constraint, you're right. Embedded platforms frequently operate under strict very unforgiving power and energy envelopes. But this is exactly where the minimalist filtering becomes an architectural superpower.
Okay, I'm intrigued.
By filtering out the predictable baseline locally, the edge device actually frees up its limited compute cycles. It isn't wasting all its energy continuously packaging and transmitting raw data over a network, and it isn't wasting its memory storing redundant baseline operations.
Right, because writing to storage takes power. Sending data takes power.
Exactly.
Yeah.
So instead, it focuses its limited, precious processing power solely on recognizing the statistical outlier. You are basically taking a 50 gigabyte file of pure noise, you're applying mathematical audacity, and reducing it to a 3 kilobyte text file of pure, actionable signal.
Less but better.
Less but better.
Mhm.
And in doing so, you completely restore the engineer's dignity. The machine performs the heavy, high-speed pattern matching, which, by the way, machines are mathematically built for.
Right.
And the human brain is then allowed to interpret the root cause of the failure, which is what humans excel at.
Which is such a brilliant shift. But, the implications of this minimalist approach, they extend far beyond just saving engineers from the torture of writing logs on a test bench.
Oh, absolutely.
The EDN report details how this architecture fundamentally changes the speed and the safety of how systems operate in the real world. So we're basically mapping the journey from massive raw logs in the lab to actionable real-time safety insights out in the field.
Yeah, because when these AI models execute at the edge, rather than bouncing data back and forth to some remote cloud data center, you completely eliminate network round-trip delays.
Which is huge.
It is. The EDN piece really stresses that in safety-critical systems, latency and deterministic timing are not like optional features. They are strict, non-negotiable design requirements.
And when you say deterministic timing, you mean?
It means knowing exactly how long a system will take to respond to a specific input every single time, without exception. If an industrial safety system relies on the cloud to process data and send back a command, it is completely at the mercy of network traffic.
Right.
A slight drop in internet connectivity or just a weird routing delay that could postpone a critical safety response by seconds. And in the context of heavy machinery or, electrical infrastructure, a delay of seconds is lethal.
Lethal. And the EDN report provides a really fascinating example of this with indoor circuit breakers.
Yes, the arc fault example.
Right. So we rely on high-energy electrical switches in our homes and factories to detect dangerous arc faults. And they need to trip before they cause an electrical fire. But an arc fault is incredibly difficult to detect because the electrical environment in a house or a factory is actually incredibly noisy.
Very noisy. Because an arc fault occurs when electrical current jumps across a gap.
Right.
It creates a highly concentrated thermal event, basically a super hot spark.
Right.
The problem is, many perfectly safe household devices, like, say, the brushed motor inside a standard vacuum cleaner, they naturally create small electrical sparks during normal operation.
Okay, so if you look at the electrical signature of a vacuum cleaner motor and a lethal arc fault.
They share very similar high-frequency noise patterns. They look almost identical to simple sensors.
Wow.
Yeah. So traditional threshold-based circuit breakers really struggle with this. If the threshold is set too low, the breaker generates constant false positives. It literally trips every time you turn on the vacuum cleaner.
Which is incredibly annoying.
Right. And human nature dictates that if a safety device constantly gives false alarms, the operator will just bypass the breaker entirely.
They'll just tape it open or replace it with a dummy switch.
Exactly.
Right.
Which completely defeats the safety mechanism. This is exactly where local anomaly detection becomes life-saving. By deploying an AI-based trigger at the edge, directly inside the physical breaker panel in the wall.
So no cloud at all.
No cloud. The system uses a localized model trained specifically on the Fourier transforms, the actual frequency signatures of lethal arcs versus harmless brush sparks. It analyzes the waveform in real time, differentiates the safe noise from the lethal anomaly, and trips the breaker instantly.
Because the intelligence has to be immediate and it has to be local. A circuit breaker simply cannot wait for a Wi-Fi connection to ask an Amazon server if the house is about to catch fire.
Exactly. It's an absurd concept when you really think about it.
It is. And the second example the EDN report highlights is automotive safety, specifically in-vehicle occupancy sensing.
Right. Detecting if a passenger, particularly a child, has been left in the rear seat of a vehicle. This is a highly complex sensing challenge, because to do this reliably without getting false positives from, say, a heavy backpack or a bag of groceries, the vehicle needs to process high bandwidth data.
Like what kind of data?
Things like millimeter wave radar, very sensitive acoustic patterns, or even interior vision data.
Okay, but streaming continuous interior radar or acoustic data to a cloud server over a cellular network just to determine if a child is in the car, that is a complete non-starter.
Totally.
I mean, you cannot guarantee cellular coverage in an underground parking garage, and that is exactly where this system is most likely needed.
Furthermore, streaming that level of personal data to the cloud introduces a completely unacceptable privacy risk. Nobody wants a live microphone or radar feed from their car streaming to the cloud 24/7.
Oh, absolutely not.
So an edge-based architecture solves both the latency and the privacy issues simultaneously. A contained on-device edge system analyzes the high-bandwidth radar data locally. It identifies the biological micro-movements of a breathing occupant, like the tiny rise and fall of a chest.
Wow.
It registers the anomaly of an occupied vehicle that has been turned off. It triggers the local alarm, and then it instantly deletes the raw radar data.
So the data never leaves the physical cabin of the car.
Never. It is the ultimate execution of RAM's less but better. It preserves battery life by not transmitting heavy data. It ensures deterministic timing by removing network latency, and it guarantees absolute privacy by vaporizing the raw data the literal moment the actionable insight is extracted.
It's just brilliant. So if this edge architecture successfully strips out the cloud latency and frees up all this compute power, the immediate byproduct isn't just engineering sanity or physical safety, it is actually a massive reclamation of raw capital.
Huge amounts of money.
Let's trace where that money is actually leaking within the corporate structure today.
Well, the industry analysis points to this as a full-blown crisis of enterprise efficiency. They estimate that resolving these technical bottlenecks translates to million-dollar savings per product cycle.
Per cycle.
Yeah, because when you force a senior embedded systems engineer to spend 4 days hunting for a single syntax error or a voltage drop in a 50-gigabyte log file, capital's leaking directly out of your operational budget in two very distinct ways.
Okay, break those down for us.
First, you are paying a premium engineering salary, someone trained to design complex architectures, someone making maybe 200 grand a year to execute biological pattern matching.
Which a machine could do for pennies.
Exactly. It is like hiring the world's most overqualified, expensive proofreader and forcing them to hunt for a single misplaced comma in a 10 million word document.
That's such a great analogy.
Right. But the second, and honestly much larger link, is the opportunity cost. While that brilliant engineer is scrolling through hex strings for a week, your product is sitting stagnant in the laboratory instead of shipping to the customer.
It's just burning money.
Burning it. By embracing AI as a local log co-pilot, product shipping timelines compress dramatically. When the machine handles the mathematically heavy pattern matching, the human is instantly freed up to execute the complex mechanical repair. You stop wasting brilliant talent on robotic tasks, which accelerates the entire research and development pipeline.
You know, what I find so compelling about this specific moment in the industry is the cultural shift surrounding it. The sources point out that professionals are no longer just quietly hiding these inefficiencies.
No, they're getting very vocal.
They are. They are moving away from that sanitized corporate public relations speak. And they're taking to platforms like LinkedIn and Medium to share unvarnished, totally raw accounts of these systemic failures.
Oh, the postmortems on Medium are incredible. You see these detailed write-ups of how a single poorly designed logging architecture delayed a major hardware release by like 6 months.
Wow.
And these viral, highly technical discussions, they expose the massive dissonance between the clean, green checkmark dashboards that get presented to the C-suite.
Oh, right. The executive summaries.
Yeah. Versus the messy 50-gigabyte reality of ground-level execution. Executives are finally being forced to realize that their legacy testing benches and their defensive data hoarding policies are actively draining their R&D budgets.
Because the executives demand rigorous testing, but the operators are the ones who have to absorb the physical and mental pain of that rigor.
Precisely.
So, okay, if you are listening to this right now and you manage a QA team, or maybe you are an engineer actively dealing with this exact data hoarding nightmare on your bench, how do you actually build this minimalist architecture? How do you bypass the procurement gridlock and those terrified compliance officers?
This is where Prasad Bond's manifesto really shines, because it provides a highly specific practical implementation protocol. He calls it the 48-hour actionable validation signal.
Catchy.
It is. And he emphasizes that the entire strategy relies on executing this within approved IT sandboxes, requiring absolutely zero policy violations.
Catchy.
It's the whole ballgame. You don't have to ask the compliance officer for permission to change the centralized database policy because you are filtering the data before it ever leaves your local bench. You aren't touching their data lakes.
Okay, so let's look at how an engineer actually sets this up. Because the physical aesthetic of this solution, as described in the sources, is pure DRAMs.
Oh, it really is.
You start with the physical setup. You locate a historical test log, let's say a 10 gigabyte file of raw output, and you put it on an improved offline engineering workstation. You disconnect that machine from all external networks to guarantee strict security compliance.
No Wi-Fi, no Ethernet. Completely air-gapped.
Right. Then you attach an approved offline computing module directly to the hardware-in-the-loop bench computer.
And the visual description of this setup in the sources is just striking. It is a complete and utter rejection of modern, glowing, touchscreen tech aesthetics.
It is entirely austere. Just imagine this. A matte off-white workstation sitting in vast negative space. In the center, there is a raw, exposed, printed circuit board interfacing with these heavy-duty testing probes. Thick, braided gray cables route the physical connections out of frame.
Very utilitarian.
Yeah. And the local processing unit sits adjacent to it. It has exactly 2 physical tactile toggle switches. There are 0 glowing digital overlays, 0 touchscreens demanding your attention. It is the absolute epitome of physical engineering reality. It is functional clarity in physical form.
It's beautiful, honestly. And the software implementation provides that exact same functional clarity.
Walk us through the software side.
Okay, so the core of this protocol is a lightweight Python script. The engineer writes a script utilizing standard pre-approved libraries that are designed to parse the massive log file. But the challenge here is you cannot simply command a standard Python script to open a 10 gigabyte file.
Oh no, if you try a basic with open command on a file that big.
It will instantly crash the system's RAM. Your machine just locks up.
Exactly, and this is where the coding mechanics become really elegant. To bypass those standard memory limits, the script utilizes memory map file support, specifically the limmap library in Python.
Right.
Instead of loading the entire 50 gigabyte hex string into active memory all at once, mmap basically tricks the operating system into treating the massive file on the hard drive as if it were a direct block of RAM.
Which is incredibly clever. The script processes the data in tiny, localized chunks. It yields data through generator functions rather than storing it all in a giant list.
Right.
This allows the script to parse a massive file while executing in under 200 milliseconds per chunk. So it's operating entirely within the thermal and memory constraints of that tiny offline module.
So once that pipeline is established, you train what Bond calls the mathematical envelope.
Yes.
You configure the script to calculate the standard operating deviation of the machine, you command it to recognize those baseline I am fine repeating cycles, and you instruct the script to drop all normal operating data instantly.
Don't save it, don't flag it, just let it vanish.
Exactly. It isolates and saves only the statistical outliers.
And the impact of this workflow redesign is measured on Monday morning.
The moment of truth.
Right. The engineer arrives at the lab, but instead of a crashed text editor and a 50 gigabyte file of garbage, they receive a localized 3 kilobyte report detailing exactly 3 or 4 anomalies.
Wow.
They can look at the timestamps, cross-reference the voltage drops, and identify the root cause of the hardware failure in 15 minutes instead of 3 weeks.
That is life-changing for an engineer. And then you measure those reclaimed human hours, you calculate the premium payroll saved, and you present that localized impact metric directly to leadership.
That's how you win them over.
Exactly. By applying mathematical audacity, engineers can completely redesign their workflow from the bottom up. They bypass bureaucratic gridlock by simply designing a better, minimalist, localized filter.
It really represents a profound shift in how we value human attention and cognitive bandwidth in the workplace. We stop using highly educated engineers as brute force biological search engines, and we finally allow them to return to the complex work of actual problem solving.
Less, but better.
Always.
Well, let's summarize the overarching journey we've explored today. We started by looking at the staggering inefficiency of modern firmware testing, that 50 gigabyte blind spot that basically guarantees human failure and crushes engineering morale.
And we trace the root of that hoarding to corporate compliance fears, legacy hazing rituals, and procurement gridlock.
We then explored how Edge AI acts as the ultimate minimalist filter. By applying Dieter Ram's philosophy of functional clarity to data, we can process massive data streams locally, instantly deleting mathematically redundant baseline data.
Which is huge, Because this architecture not only reclaims engineering dignity, but it provides the deterministic timing required to operate real-time safety systems.
Right, like those indoor circuit breakers and automotive occupancy sensors we talked about,
Hmm.
all functioning without the lethal latency of the cloud.
And finally, we saw how this localized intelligence prevents massive capital leaks, saving enterprises millions of dollars by accelerating product shipping timelines and letting machines do the heavy pattern matching. We completely streamlined the design of testing architectures by ruthlessly removing non-essential data processing.
It is a perfect synthesis of mid-century physical design principles solving 21st century digital architectural failures.
Truly is.
I want to leave you with a final thought to mull over today, something that builds on this entire concept of the mathematical baseline. If information theory dictates that perfectly repeating machine cycles contain zero information,
Right.
and if local edge AI can now seamlessly delete this predictable baseline from our complex engineering logs, what other areas of our daily personal human workflows are just predictable baselines waiting to be filtered out?
Well, that's a great question. If we stop manually hoarding and parsing the noise of our own digital lives, what might we finally see?
Exactly. If we actively applied Dieter Rams' philosophy of less but better to our own cognitive loads, what essential critical signals might we finally have the bandwidth to recognize? What is your personal 12 millisecond voltage sag that you are currently missing in all the noise? Thank you so much for joining us on this deep dive. We will catch you on the next one.